Stan Gibilisco here with Chapter 3 in the Tale of Two Antennas. A little more theory for you here. The other antenna, I described the active tuning antenna system by Yaesu in the previous chapter, Chapter 2. Now I'm going to show you the theory as best I can for the 8-foot whip antenna, once again at a frequency of 7.035 megahertz. In this case, this is an untuned antenna, so we have an SWR on here, on this feed line, that's something horrible. But this transmatch, a PAL Star AT500, can tune that mismatch, whatever it is, to a 1-to-1 standing wave ratio for the Yaesu FT857D. So the Yaesu FT857D sees exactly the same thing with this antenna when it's tuned with this transmatch here as it sees with the automatic, the active tuning antenna system by Yaesu, where the tuning takes place at the feed point, which is a much better place in theory for that. However, this antenna is a little bit longer than the active tuning antenna system. Let's look that up. Once again, in the handbook of radio and wireless technology published by yours truly in the 1990s. We'll go to page 111. But first, I'm getting ahead of myself. First, I've got to calculate for you how much of a wavelength this antenna actually measures when it's 8 feet long. Remember, on 40 meters at a 7.035 megahertz, a wavelength is about 140 feet, very close to 140 feet. So we're talking about 8 divided by 140, or 0.057. 5.7% of a wavelength. Still a mighty short antenna. Now let's go to that table, or that chart, that graph on page 111 of the Handbook of Radio and Wireless Technology. 0.057 is just past that first hash mark there. So we're talking, if we're lucky, about a radiation resistance of 2 ohms. Remember once again that the radiation resistance plus the loss resistance has to equal the resistance that we see with a 1-to-1 SWR, resistance equivalent or equal to the characteristic impedance of that line, which is 50. However, in this case, the radiation resistance equals 2 ohms, so the loss resistance has to equal 48 ohms. So how do we calculate the efficiency of this antenna, assuming that we don't have to contend with any loss in this line? But that's not the case. But I'm going to ignore that for the moment. Let's just suppose then that we had some kind of a line that would get rid of that loss. They do make a type of line now. I believe it's called monax, as opposed to coax, which actually eliminates reflected power. It's a very interesting thing. Look it up on Google. Google it. It was in QST for the upcoming month, for April. I sure hope it wasn't an April Fool's article. I just thought of that right now. But anyway, what we got here is 2 ohms of radiation resistance and a total resistance, the radiation resistance plus the loss resistance, of 50 ohms. So we're talking here, the efficiency is this radiation resistance divided by the total resistance, which turns out to be 4%. Well, that beats the active tuning antenna system, doesn't it? Well, no it doesn't, because we're not using Monax here, whether it's for real or not. We're not using it. I'm beginning to suspect that this might be an April Fool article, because they were talking about this Monax stuff actually producing gain. I don't know how a transmission line can produce gain. I don't see it. I just don't see it. It's like exceeding the speed of light. I just don't see it. But what we got, but maybe it can, I don't know. We'll see. If I can get a hold of some of this stuff, if it's for real, I'd love it. Sure would help right here in a situation like this where the SWR is probably 20, 30, 40 to 1. How can this transmatch deal with an SWR that high, you might ask? Well, I think that's because of this loss resistance right here. If it weren't for that, if this were 0, then you would have a 2 to 50 standing wave ratio, or 50 to 2, 25 to 1. But as it is, it's probably not quite that bad. Well, it'd be worse than 25 to 1, because you do have reactance here as well. And so I couldn't find the charts for this to calculate how much loss a 20 or 30 or 40 to 1 SWR would cause on 13 feet of 50 ohm RG58U coax. I couldn't find the charts. And anyway, I don't even really know this SWR. But if in the worst case scenario, this is a 3 dB loss in addition to over and above what we would get with this. Remember, the active tuning antenna system allows for a 1-to-1 SWR on this length of line. This arrangement doesn't. It gets rid of the problem at the radio. Now, the radio doesn't know the difference, but the airwaves will. If it's 3 dB of loss, and that's I don't know, it's probably around that, then really we're only getting the equivalent of about a 2% efficient antenna, because we're losing half of this 4% that's originally getting there. So the active tuning antenna system ought to win. The ATS ought to beat Gibilisco's contraption on 7.035 megahertz. And the noise that I hear on that antenna certainly indicates that that would be the case, but I haven't actually tested this thing in real life yet. I haven't made a contact and compared them side by side. But a colleague of mine, Herb, has, and I forget his call, God bless it, but he's going to call me tomorrow on 7.025 megahertz, and we'll see what happens. If that doesn't work, he's agreed to try me on 10.110 megahertz 15 minutes later. That's called a sked. Remember skeds? I don't know if that... Did we still do skeds? I guess we must. Anyway, let's find out what happens. Let's find out what happens. The automatic tuning, the active tuning antenna system ought to beat my contraption. If you want to learn more about me, you can go to this website, sciencerator.net. You can see all my videos by clicking on the videos link, and you can see all my books by clicking on the Amazon link, and you can see a whole lot of other baloney by clicking on the other links. For now, though, Stan Gibilisco, Whiskey 1, Golf, Victor, or Good Vibrations. Signing off until the test shall begin tomorrow, which by the time you see this video might be a long time ago. 73, and so long.